All right, good morning. My name is Charles. MemVerge is proud to be the new member. We are also a sponsor. This is our first marketing expenditure of the company. We don't have a marketing person yet, but so we've been around for 2.5 years, and over the last couple of years, been working very closely with Intel as our whole company was started to develop software on persistent memory. And before this, I worked at VMware for quite a few years, quite a few VMware colleagues here. I was managing the storage team, and I learned quite a few things at VMware, and I think one of them is VMware does have Intel to thank for their success. You know, if you go back to 20 years, if you remember, Intel CPU start to taking a different direction. Instead of going faster and faster, you start to have more and more cores into the CPU. And it's a great technology. It's one of the reasons the cloud and data center is so powerful today. But at that time, one of the difficulties was the applications were not programmed to so many cores. The threading model and all that are not ready to take advantage of this new hardware. As a result, the server utilization was not that high. And some applications they try to rewrite, but it's not easy to convince every application to rewrite, to adapt to this new hardware. So this is where VMware came in. It created a sort of a middleware, a virtualization layer, abstraction layer, that creating an API that's compatible to the hardware, yet you can have many of them sitting on the same servers. So you do not have to rewrite your application, and yet you can take advantage of all the cores that's available in the new hardware. And as a result, the utilization go up, and that got VMware started. And of course, it developed many other things afterwards, but this became a powerful software layer and create a new software market that also helped the adoption of this great new hardware in the data center. And it's our belief we are in the same situation here, or similar situation here, where persistent memory is a revolutionary new technology that redefined what was known as memory and what was known as storage before. And it presents new APIs, and certainly there are applications that are rewriting to take advantage of this new hardware, such as Soji presented earlier on. But the reality is that not all workloads, not all applications are going to rewrite. The question is, how can we get all those workloads onto this new hardware and take full advantage of it? And that's a mission we have. So our mission at MemVerge is try to create a software layer that's designed for persistent memory. Yet it presents API that's easy for application to consume, including existing application without rewrite, that they can start taking advantage of the bigger scale of the memory service the persistent memory provides, and the persistence of this memory speed storage that can take over the I/O of the applications transparently. And we can do so at the same time, software-defined, dynamically reconfigurable between those APIs. So that's the layer of software that we are developing. And I'm happy to introduce some initial, our initial version of the software, its design, and some of our initial use cases. So the space that we're targeting is the intersection between big data and fast data. We believe that's sort of lower hanging fruit where persistent memory will find its most compelling use cases. As we know, we are living in the age of data, and the word of big data has been around probably for more than 10 years now. And there are a number of good solutions on the market today to address big data. You can scale to many petabytes of storage. There are hardware solutions, there are software solutions. You don't need another solution for that. But there is a limitation to those solutions, and that is latency. A typical latency of a big data solution are in the order of milliseconds. And the fastest can go to maybe hundreds of microseconds in terms of latency, but no shorter. And that's partly limited by the underlying media that's available to power those big data solutions. So it's good to scale, but not so good with speed. Now, so what do we do with speed? So there are also a number of solutions that handle low latency situations. And those tends to be more DRAM centric. in the space of low latency trading or in AI or even in big data. There are more and more applications that's DRAM centric. They keep more and more of the processing all in memory. In those situations, you can't go to low latency. You can go to microseconds or even nanosecond level latency. But you have a scale problem because DRAM naturally is limited to the amount that's available to the applications, typically on the hundreds of gigabytes per server range. Now, what happens if you need both? And fortunately or unfortunately, there are more and more use cases where you need to deal with both petabytes of scale and nanosecond or microsecond of latency at the same time. And there's not a good solution to address those use cases. And there are more and more such use cases available. And we believe this is one reason persistent memory came at the right time, because it does have the scale that's beyond the scale of DRAM. It does have the speed that's way faster, or latency that's way faster, 2 order of magnitude, or maybe 3 faster than the fastest SSD or NAND flash that's available today. So that provides a good foundation where we can build a solution that can address both big and fast data at the same time. And I'll probably go fast on this slide. I think the previous speakers know this much better than I do. The only thing I want to say is I do think it's a groundbreaking product. It's 20 years into working, and we believe it's just a beginning. Today, or this year, I think is year 1 of persistent memory. And it will have a long and happy life ahead of it. And we are happy to be a first mover, kind of creating the software on top of it. I think there will be more people like us. And I think this will be a vibrant ecosystem, and happy to welcome more friends to do things on top of this new amazing technology. And then diving into what we do at MemVerge, the software we developed, we don't have an official name yet. We need to hire a marketing person to name the product. The technology is called distributed memory objects, which I'll go into more detail in the next slide. And our main purpose, if there's some marketing person, feel free to apply here. And let me know how you want to name it after the talk. In one sentence, what we try to deliver, at least in the first version, is try to deliver bigger memory and faster storage at the same time without requiring application changes. Now, you could do some of it certainly without us. As the previous speaker introduced, you can, if you just want to be compatible with memory, there's a memory mode that you can use. If you just want to be compatible with a block storage, there's a app direct storage mode that you can use. But if we want to use both at the same time and dynamically reconfigurable without changing applications, there's not an easy way of doing it. If you're just using app direct, the persistent memory programming model, it is a new API. You do need to program to it. And so the first module we did is what we call memory hypervisor. This layer essentially access persistent memory in the app direct mode. We actually use PMDK that Andy and team developed and to access and manage the persistent memory across a pool of servers. And yet to the applications, northbound, we present various storage and memory APIs that are compatible with the APIs today. And these are software APIs so that they are flexible, they are sort of composable, and dynamically reconfigurable. And so essentially we are a translation layer, we are an abstraction layer. We talk to the persistent memory in its native mode, and we present compatible API to the applications so that they don't have to rewrite. So that's what we meant by the memory hypervisor. The hypervisor in quotes because it's really different from VMware or KVM hypervisor. It's really do a protocol translation on the memory or data front. And above this hypervisor, and behind those APIs, we developed 2 interesting systems. The first one is a distributed file system that is optimized for persistent memory. There are many distributed file systems out there. Probably last time I counted, there may be 24 of them. Some of them open source, some of them proprietary. So the world doesn't need another one, except there's not a distributed file system available today that's optimized and designed for memory. And we believe this is the first of such kind that is designed from ground up for persistent memory and deliver storage services to the applications. And this is a sure nothing distributed file system running on servers. And behind the memory APIs, we also developed a tiered memory system. Essentially, it's a memory system that has 3 tiers. There's a DRAM tier, there's a persistent memory tier, and both of these are local. And then there's a third tier that is memory that's available on the other nodes in the cluster through some kind of network. Today, we use RDMA, most commonly RoCE, RDMA over Converged Ethernet. In the future, there could be over CXL or other memory fabric across the servers as well. So we developed a distributed clustered tier memory system behind that memory API. So the combination of those 3 components essentially does what I described. It takes full advantage of the properties of the persistent memory underneath across a cluster of servers, and they present them to be available to the application in both memory APIs and storage APIs, so that the application do not have to change, and they really have the best platform for their working set of data. And that has a latency on the order of hundreds of nanoseconds if it's local, single-digit microseconds across the cluster, and it can scale across the cluster to hundreds of terabytes of memory. So the next slide will give you a bit more details of what I described, as well as some of the initial use cases that we are addressing. Our software is in beta today, so we have not officially shipped our product yet. I guess we need to have a name to ship the product. But we do have a few customers. We have about a dozen beta customers who have been working with us in proof of concepts and running this in their environments. And so on this picture, at the bottom, you see the compute nodes. Those are servers. And we are software-only product, so it can be any servers from any of the server vendors. Inside the servers, there are persistent memory, but there could also be DRAM inside the same servers. There could be SSDs inside the same servers as well. They are interconnected by some low latency networking. As I described, we recommend RDMA networking. And our software is this blue box between the application and the servers. And the APIs we provide to the applications include a POSIX-like file system that essentially the application can just use as any VFS on Linux. So we are a user space software running on Linux. It can run on physical nodes. It can also run inside of virtual machines. And we actually have a demo that for us running on top of vSphere inside of vSphere VMs. And it can also be deployed on the cloud after the cloud have the persistent memory available in their infrastructure as well. And the APIs we provide, as I mentioned, on the storage side, we have a POSIX-like file system API. We have an HDFS API that for anything that's talking to HDFS today, they can just talk to us instead. And the reason we support this protocol first is because some of the use cases we targeted first in big data analytics, in machine learning, AI training, HDFS API is a popular API that they use. And we do have our SDK, so for those who do have control over their software, they can certainly link to our SDK and call our function calls directly as well on the storage side. And on the memory side, they can certainly use our SDK to allocate and deallocate memory that way. But we also have other ways to intercept the memory functions through LD preload. So we would intercept the various memory allocation calls into our system so that we handle the memory allocation and place them on the right media underneath in our tier memory system. So this allows us to work transparently with applications that they do not, if they wish, they do not need to change their applications and yet readily can use us both for their memory and for their storage I/O. The key application, I mentioned a few, they're machine learning, TensorFlow workload. We're working with some customers with TensorFlow. Their big data, analytics workload. We have quite a few Spark deployments among our PLCs. And we also have recently have a version of RocksDB that works well with persistent memory. And we also use that RocksDB as a storage engine for MySQL and MariaDB so that we have a clustered MySQL deployment with a customer that increase their credit card processing by at least 3 times in terms of transactions per second. So there are some use cases there as well. But what's most exciting for me in the last few months is we start working with quite a few financial customers on Wall Street, particularly for their trading infrastructure and for their market data infrastructure. There are quite a few use cases that can really enjoy, I think, these exciting new properties persistent memory and our software bring to those use cases. So I'll give some examples of these use cases. The first one is a big data analytics use case, and this is us working with a cloud service provider. This is a cloud data warehouse service built on top of Spark SQL that runs on top of a cluster of Spark nodes. In fact, I think last year at Persistent Memory, we gave a talk invited by Intel that went into, I think we co-presented with Tencent, if I remember correctly, on this use case. And this is exactly their use case. This is actually, we creating a DMO cluster, that's the Spark accelerator on the side. They have a Spark farm that can scale to a couple of thousand nodes. We basically move all their intermediate data from a Spark, including RDD data, including shuffle data, all onto our nodes that in turn not only did not slow down the performance of the Spark queries, but actually speed it up. Here are some examples. Terasort with RDD caching speed, they're 5x or 7x of performance speed up. And also through this process, we move those intermediate state away from the Spark cluster so that the Spark farm become more elastic. It's become more stateless and elastic, and that is desirable for this particular cloud service provider. So they liked us for the performance speed up as well as for the removal of the state from their core resources. So this is one example of us using DMO plus Optane DCPMM to deliver for a Spark use case. A second example is us working with a social networking company based in the US. And it is the infrastructure for AI training behind their recommendation engine. It's running TensorFlow with a model called Wide and Deep. And Wide and Deep is a popular model for recommendation engines. And one thing with recommendation engines, the model is not necessarily very deep. It's not like image recognition or say, oh, you have many layers. But it's very big. It's very, it actually takes many terabytes of memory space to just have the model itself. It has many, many parameters. It's a very sparse model. And the training data itself is huge as well. They have over 600 million users. So that's the edges. And you have many billions of edges, which are the connections between those users. And you need to feed all those data into this huge model over 1,000 times in order for the parameters to converge. And so that you can making the recommendation on the people you may know, or maybe the job you may want. So this is the core service for that social networking company, and the training typically takes couple weeks to complete, and it takes a cluster of servers because of the amount of memory it needs to have. So there are a couple problems. One is just the speed of convergence, and the other is that because there are more than one servers, the chance of failures is high. How do you recover from the failure become a problem, because if you lose a node, they need to restart the training from 2 weeks ago. So that's a lot of waste of resources and time. And by replacing the local drives, the HDFS they are using with a DMO system, that we are able to achieve up to 6 times improvement in the length of training. So what used to take a couple weeks now takes a little more than a couple days. And just the storage importing from various data sources into the system sped up a lot, just because the previous system wasn't that fast in getting the data in. And most excitingly, that we can perform checkpointing much more efficiently. One particular sweet spot, we believe, for persistent memory is efficient checkpointing, because checkpointing is where you copy the data from memory to a persistent store, and in order to save the memory state so that you can recover from it in case of failure or for other reasons. And now with memory itself being persistent, there are various ways we can optimize that process. And not to mention the speed itself is much faster. So we have a capability that can do very fast checkpointing that really made the failure recovery more graceful in this use case. So that's a second use case, a AI training use case. The third is a group of use cases I just mentioned. These are with the financial customers. This is not yet with their mainstream infrastructure, their vSphere setup yet. This is with many of these financial institutions, they often have a corner where they have their low latency infrastructure to support trading and support fast, high performance market analytics, market data analytics. And that's sort of a niche, but it's a big niche. And there are a lot of value associated with that infrastructure, and that often is the early adopter of a new technology as well. And we've been working with quite a few customers, including hedge funds, quantitative firms, banks, investment banks, as well as the exchanges. In some of these use cases, we're working with some applications such as KX, which produce a time series in-memory database. And then we support KX, we support a few other databases, and we support in-house applications that they develop for this also. So generally, we found at least 3 areas the persistent memory and our software has a potential value to add. The first one is sort of in what they call the back testing. So what back testing means is for people with quantitative researchers or quants. They invent new models and they need to test the models. And the first way they test the model is using historic data. So they usually have a storage that takes a few hundred terabytes or 1 petabyte of market data on some NAS system or some distributed storage system. They use a KDB or some other solution or their own solution to be able to query a subset of those data that serve as the input into their model, and then they take the output of their model for prediction and check with the actual historic data to see how well they match. So that's a very common way for quants to validate their models. And now if you have a lot of quants, the storage become a big bottleneck in performing these backtesting jobs. And for our system, we can providing a much faster system. So the existing state of art is they keep certain data in DRAM, but not a lot, and most data in the storage system. Now with our system, we can creating a layer that's bigger, that can take more of the data and deliver it much faster to these quants, so improve the backtesting efficiency. And then there's a pub/sub service. This is a more real-time. This is very important for the exchanges as well as with some large banks. As the market trades are happening, those ticker data coming in, and they have a sequencer that's writing them down. And then at the same time, they have many other processes need to consume this event stream, which are these trades that come in at a high rate, and they want to deliver to these many processes with low latency and with good fairness. And And to do so, there is an existing system using some kind of multicast on solar flare, but at the same time, they need to persist it at the same time onto the storage. So we are delivering a new solution based on DMO that essentially using the combination of the obtained DCP-MM and the RDMA Mellanox network, and having a new mechanism to allow this data to be shared across could be 100 different processes that are consuming this event stream. So that's another use case that we are very excited about, and we are validating that with some of these customers. And the third one is working with KDB, both in accelerating the KDB performance, but also potentially to help KDB in the crash recovery use cases as well. So we're working on a partnership there. So those are some of the financial use cases that have emerged recently and we are pretty excited about. So at the end, this is my last slide. So let me just give you my high-level view of where the future holds. I'm sure here many people share this view, and some people might know this to a higher granularity than we do. But let me just share with our view here. Our view is in the next 5 years, we believe it's going to become obvious to everyone, not only to the people in this room, but to everyone that persistent memory is here to stay. And it's going to be an important component of a data center. In fact, thanks to persistent memory, DRAM is not going away. It will continue to exist. But a combination of DRAM and persistent memory, we believe will create a new memory tier. Right now we call it MCI. We call it the Memory Converged Infrastructure. You can give it any other names, but it's a new memory tier. As a result, the data center will become more memory-centric. And what do I mean by that? Is that this memory tier will be very different from today's memory tier. Number one, it's going to be much bigger. We believe it's going to go to hundreds of terabytes per server. Yeah, certainly Intel and others need to work hard on that. But we think it's going to go to hundreds of terabytes per server, and the cost will be going down. And imagine, as an application developer, you have 100 terabytes of memory available to you per server. That just opened up the new world for you, how the new application can be developed, how they can be optimized, how they can be deployed. So that's going to change the application world. And secondly, it will be persistent in itself, this memory tier. It's big, it's cheap, and it's persistent. So what that mean is if you have the right layer of software that to go with this memory tier, deliver the right data services directly on this memory, the primary performance tier storage as we know it today may no longer be needed, because all those functionalities we are relying on primary persistent memory, primary performance storage now will be performed and fulfilled from a memory tier themselves. And that's going to be a big shift to the industry as well. So this is very exciting. And we are here to deliver this software tier. And we will not be the only one. I think there will be others who join us. But I think there's a great future that's going to move tens of billions of dollars around in this industry. And we are glad to be a first mover and look forward to this journey together with all of you. Thank you.
In your summary, you just said that DRAM was not going away, and then you said the memory tier may no longer be needed. I don't know how to reconcile those two statements.
Sorry, maybe I had a typo, or so I think what I meant, and that's, so what I meant is the primary performance tier storage layer may no longer be needed, not the memory tier. So I think the memory tier will become bigger, and it's going to take over the data center. And the storage as we know it today, and by the way, if there are storage people in the room, it's not meant to be offensive. I think the function will still be needed. It's just the form factor, I think, will look a little different. So the data center today, I'm a storage person also, so the data center today is you have servers. Server have compute and memory inside, and then you have performance tier of storage. Those are now more and more all flash arrays or so on. And And then they have capacity storage either on-prem or in the cloud that give you, a lot of scale. So, and they are interconnected by various kind of networking. So that's sort of, from a certain perspective, how the data center looks like today. In the future, we believe this memory tier will become bigger, more powerful with the right data services, and answering to the data persistence needs or for active data directly from the servers. So the green part will be the sort of the new server racks, and there'll be potentially new memory fabric interconnecting them. And that layer might answer to all your data needs. So the performance tier storage, as we know it today, may no longer exist. So that's what I meant. Yes?
One more. Can you wait for me to come to you?
Yeah, I think I heard it. So the question is whether it's an appliance model, whether it's or else. So we are actually not an appliance model. So we are a software-only model. So our customers would, and we noticed a shift in customers' sentiment also, that they like to standardize on their server infrastructure from their favorite server vendors, or having a right bidding process between the server vendors, and our software work on all of them. And so it's sort of a VMware model where it's a software only running on all major leading server platforms, or on the cloud as well. And we are licensed based on we haven't finalized the licensing model, but we are licensed. Our current thought is we are licensed on the amount of persistent memory that we manage, and it's transportable between cloud or on-prem.
Right, I think we have one more.
Yeah.
There is a difference between endurance of a volatile memory like a DDR and a non-volatile or persistent memory here. So if you think of, if there are hundreds of millions of read writes to a DDR, the DIMMs will still work after 5 years or 10 years down the stream.
Right.
But if you do the same workload on a non-persistent, a persistent memory, you may probably brick the device within few
That's right.
years.
So the endurance of persistent memory is significantly less than DRAM.
Absolutely.
And so that's why it's just like Intel memory mode, which is really a two-tier DRAM with PMAM, where DRAM absorbs many of the write cycles. And similar with our tier memory design, where we do have a DRAM tier in our tier memory service, where that will absorb many of the write cycles from the applications, so that the persistent memory write cycles will be enough for that.
So if you have questions for Charles, please visit him in the MemVerge booth over lunch and at the break.
Yes, we do have a booth, given that we spend the marketing dollars, and, and we have some demos. So.